Bonus, how did we get the logistic growth equation from dp dt? So in order to get that, what I'm going to do is I'm going to show you a little bit of something that you learned in honors pre-calculus. It is called partial fraction decomposition. So, for example, if I had a problem like 1 over x times x minus 2, and I wanted to break this down into two different fractions, I could break this down into two different fractions, and I need to figure out what the coefficients of those numerators would be. So essentially what I do is I figure out what each of the denominators is missing and multiply the numerator and denominator by that, and then I have a common denominator so I can kind of get rid of it. So the denominator in the left side is x times x minus 2. When I multiply through by x times x minus 2 in the whole problem, that's going to go away. When I multiply through by x times x minus 2, this term becomes a times x minus 2, and this term becomes b times x. So now what I have is I have ax plus bx minus 2a equals 1. And then what I can kind of do is figure out exactly what is going on here. I have a plus b x minus 2a equals 1. Now notice that 1 is really 0x. So I have a couple different things that I know. I know that, 1 is really 0x plus 1. So I have two different things that I can kind of match up. I have 0x must equal a plus bx because they're on the same side of the equation, or they're in the same part of the equation, and I have 1 equals negative 2a. So I can say 0 equals a plus b, and 1 equals negative 2a. So I solve, I get a equals negative 1/2, and then when I substitute this in here, I get b equals positive 1/2. So if I wanted to break this down into two different fractions, I can say that 1 over x times x minus 2 is equal to negative 1/2 over x plus 1/2 over x minus 2, which if I wanted to write it, I could write it as negative 1 over 2x plus 1 over 2 times x minus 2. So that is how you do partial fraction decomposition in its very most basic form. Okay, so now that we have reviewed that from honors pre-calculus, and I know there's a lot more to it, and when we do it as a separate topic, we'll be talking a lot more about it. But the reason why I'm talking about that is if we take a look at this differential equation, I'm going to separate the variables. So notice that p and t are my variables, c is a constant, and k is a constant. So I'm going to divide by p and c minus p, and then multiply dt over to the other side. So I'm separating the variables. Now I want to integrate. The integral of the right side is really easy. That's kt. And then we're going to have a plus c. The integral of the left side is a little bit more complicated. In order to integrate that, we have to have partial fractions. So if I take a look at the partial fractions, I have 1 over p times c minus p, and that equals some constant that we're going to find out over p plus some other constant over c minus p. So I can break this fraction up into two other fractions. Now, when I multiply through, I end up with 1 times a, 1 equals a times c minus p plus bp. Remember that 1 is the same thing as 0x plus 1. But in this case, our variable is actually p, so I'm going to make it 0p plus 1. So if I have ac minus ap plus bp equals 0p plus 1, notice that b minus a p equals 0p, which means that b minus a equals 0. And then I also know that ac equals 1, which means that a equals 1 over c, which means that b is also equal to 1 over c. So when I take a look at A and B. So A and B are both equal to 1 over C. So after I do all of that mathematics, I end up with A and B being replaced with 1 over C. And so now what I can do is I can take this and I can rewrite this integral as dp over cp plus dp over c times c minus p. Remember that c is a constant, so this ends up being 1 over c natural log of p plus, and p is the absolute value, but remember this is a population, so it's always going to be positive anyway. And then this one is 1 over c times the natural log of c minus p. But notice that if I did a u substitution on this, c minus p is actually going to have a negative p on the inside. So that means that I need this to be negative. And that's all equal to kt plus c. This just keeps getting more fun as we move along. So I'm going to condense and factor out a 1 over c. So 1 over c times the natural log of p over c minus p is equal to kt plus c. And I probably shouldn't have used c as the constant because there's another c over here, but you live and learn. So now we multiply by c on both sides, so we get the natural log of p minus c minus p equals the carrying capacity times kt plus some constant. Now I take e to both sides, so I have p over c minus p equals e to the carrying capacity times kt plus the carrying or some constant over here. So now what I'm going to do is I'm going to multiply both sides by cp. Notice that ckt is CKT is something that I can have here, and then I can change this to c times that constant. And then the other thing that we can remember is that if I have a constant that's added in an exponent, I can kind of change this to be some other thing. So e to the CKT is over here. Now I'm going to multiply both sides by c minus p. Remember that c is the carrying capacity. Now what I'm going to do is distribute. So I will distribute this. I will end up with c times a e to the CKT minus p times a e to the CKT. Then I will add this p back over and factor it out. So now I have 1 plus a e to the CKT equals c a e to the CKT. Now I'm going to divide. This is a lot of work. P equals c a e to the CKT over 1 plus a e to the CKT. And then what ends up happening here is I can leave it like this, or I can multiply the numerator and denominator by some constant times e to the negative CKT. And so I end up with the carrying capacity times 1 plus some different constant e to the negative CKT, and that's basically the equation that we get from that. I know that was a lot of work and nobody's probably even watching at this moment, but that's how you get that equation.